I'll start the class. So basically today we won't be handling any practical work. We'll just have a look at what we've been working on so far. I believe the notebooks for what we've worked on are on GitHub. So we are going to use that as reference for what we've done so far. Just a minute as I open that. Okay, so we've got these notebooks over here. We've got the logistic regression model for classification, and then I'll open the region lasso regression notebooks, because already in here we've got, for example, here we've got our classification report. We should have a conversion matrix, though it's not there. And over here we have our regression evaluation metrics, for example the mean squared error and the R2 score. So what we are going to discuss today is what these actually mean. We can begin. I've got these notes over here. You can have a look at them. They are straightforward and self-explanatory. What I would expect from you is to not focus on the equation, but focus on the interpretability of everything that I'm showing you with the examples that are there. So for machine learning, we usually have to evaluate the models that we are fitting, and you've seen that from what we've been doing both for regression and classification. So we have to evaluate the model. So welcome, Mike. Let me share the link for the class notes for today again. Those are the notes. You can access them from the chat. So for regression, we've got their own metrics, and for classification, we've got their own metrics and how we can interpret them. We're going to start with the regression metrics. So for regression metrics, we've got the first metric that we've been handling, and that's the mean absolute error. So for mean absolute error, this is the formula. So you take 1 divided by the total samples that you have in your data set, multiplied by your actual minus the summation of your actual minus the predicted values. So what does the mean absolute error measure? So it measures the absolute difference between predictions and actual values. So you can see over here we are getting the absolute difference between the actual and predicted values. So what are the characteristics of this evaluation metric that we have over here? So you would expect it to range in between 0 and infinity. So if you get negative values as your mean absolute error, then it means there is an issue. You'll have to check your model and confirm that it's okay. Then units, they are the same as the target variable. So for example, if you are trying to predict house prices and you've got house prices ranging in between 50k and 100k, then you would expect your mean absolute error to be in the same range. Okay, so in the same scale, I will say. So that's what we mean by saying units are the same as the target variable. And why do we use the mean absolute error? It's because this evaluation metric is less sensitive to outliers than the mean squared error. So we'll get to see what the mean squared error is all about. And it's easy to interpret. So you can see it's easy to interpret because this equation that we have over here is straightforward. Okay, let's proceed. So an example for calculation of mean absolute error will be this. So we've got our actual house prices over here. First house price is 300, second 250, third 400, and fourth 350k. Then the predicted house price 290k, 260k, 420k, and 340k. So these are the absolute differences. So for example, 300 minus 290k is 10k. 250 minus 260 is 10k. 400 minus 420k is 20k, and 350 minus 340 is 10k. And this is what we mean by absolute errors. So they can never be negative. So we are picking the highest value and comparing with the lowest value that we have. And then what we do next after we've obtained the absolute errors is we add them all together and divide by the total number of samples that we have. And in this case, our model gave us an absolute error of 12.5k. So this is our mean absolute error. So how do we predict this? So if we scroll down to the bottom, this is how we will predict that this is how we will interpret that 12.5k. So an MAE of 12.5 means that your model house price prediction on average differ by about 12,500 from the actual sale prices. So that's what we mean from a mean absolute error perspective. Let's move on to the next metric. For the next metric, it's the mean squared error. So for the mean squared error, it's basically the same equation that you had for mean absolute error, but over here you are squaring the differences that you have between your actual and predicted values. So it ranges between 0 and infinity, and then the units are square of the target variable. Okay, so what is the use of this evaluation metric? So it's used mainly to penalize outliers. So it heavily penalizes large errors that you have. Then it's differentiable, meaning it's useful for optimization. Okay, so we had this example over here. So we are going to continue with what we had up there. So we will have 100k squared, 10k squared, which is 100k, then 10k again, 20k, 100k, and then you combine those values to give you 179k for your metric for mean squared error. So how do we interpret that? So if we come back down here to the interpretation part, let me expand this. So it means that an MSE of 179 million means that on average your squared prediction error in the house prices is 175 million. So large errors like predictions off by 30k or more significantly inflate this metric. Okay, so if you have outliers in your dataset, then it means they will significantly inflate this metric, and that's the reason as to why we use mean absolute error most of the time. And then we've got the root mean squared error. So for the root mean squared error, what does it measure? So it measures the square root of the MSE, so what we had at the top over here, bringing the units back to the original scale. And when we say it brings back the units back to the original scale, we are saying that it's bringing the units back to a scale that is similar to the mean absolute error that we have. Okay, so if we find the square root of this, we get 13.2k. You can see 13.2k is close to what we have over here in the 12.5k. So it means that for this data that you have fitted, you'll have to figure out if there are any outliers and sort them out. Okay, so that's one of the main things that you'll need to do. So check if there are any outliers and sort them out. Then we've got the mean absolute percentage error, that is the MEP score. So it measures the average percentage error relative to actual values. Okay, so over here you can see we get 100 divided by the total number of samples multiplied by the summation of the absolute values of your actual versus predicted divided by the actual values. Okay, so this will give you the output in terms of a percentage, like what is your percentage error. Okay, so instead of giving you these metrics in terms of numbers like we had for the mean absolute error, over here we are getting those numbers in terms of a percentage. So it means that our model is 3.8% less accurate in each and every case. So we can check down here from the interpretation what we have. So for MEP, a MEP of 3.8% suggests that your model house price prediction typically differ by about 3.8% from actual prices, meaning that a house that is priced at 400k, the prediction for that house will roughly be off by 15,200. That's basically what it means. Okay, so that's how you interpret it. And then we'll go back to the top here. Just give me a minute. Sorry for that. Let's proceed. We've looked at the mean absolute percentage error. Next, we'll look at the R squared score. So this is our last evaluation metric for regression-based model. So the R squared score, this is the equation. So it's the sum of residuals divided by the sum of total, so that we have in our model. So the sum of residuals should be equal to the summation of your actual values minus your predicted values squared. And the other summation is basically the sum of your predicted minus actual. So this is your predicted minus your y hat squared. So it measures the proportion of variance in target variable explained by the model. Okay, so characteristics. So this number should range between 0. We can't have negative infinity. It should be in between 0 and 1. But in some cases, you can find your value being negative. But for optimal results, they should be ranging in between 0 and 1. Okay, so 1 being a perfect fit, and then 0 means a model that's not explaining the variance of what you have better. So if so this is what you will have for the calculation. So for example, the sum of totals will be this, giving you 7.5k. The sum of residuals being this, 700k. Your R squared score will be 1 minus 700 divided by the 7.5k, being 0.907. So here you will have a model that explains 90.17% of the variance of your model. Just remember, as I've mentioned, you don't need to focus on the equation, you focus on the interpretability. So if we get an R squared score of 0.97, what does it mean? Or for example, from our model, we had an R score of 0.9. It's actually 0.97. So what does it mean? If we go to the interpretability part, this is what we have. An R score of 0.97 means your model explains 90.7% of the variance in house prices. It indicates that your model is effectively capturing the main factors influencing pricing. Okay, so your model will explain the major things that are causing house prices to change. So that's what we have. Let's head over to classification metrics and discuss what they are. So for classification metrics, we usually start by the creation of a conversion matrix. If we have a look at what we created last time, you can see we extracted our accuracy and then we extracted our conversion matrix. Okay, so this conversion matrix is what is used to calculate this classification report that you are seeing over here. And it's the same thing that's used to calculate the accuracy score that we have over here. So what is it all about? So as I mentioned earlier, or as I had informed you in that class that we had, I said that the conversion matrix is like a hypothesis table where we have the true positive and the false positive, false negative, and true negative. Okay, so for example, we are trying to predict if someone qualifies for a loan. So here we've got no and yes. We've got the actual values for no and yes. So here it means that these from our data, this guy didn't qualify for the loan. Here it means they qualified. Then here it means from our prediction, they never qualified. Here it means from our predictions, they qualified. So in a case where we predict no and the actual was no, that's what we call a true negative, okay? And then in a case where the actual was no and the predicted was yes, that's a case where we call it a false positive. Then when the predicted is no and the actual is yes, that's a false negative. And lastly, when it's yes for predicted and yes for actual, that's what we call a true positive, okay? So TP is true positive, TN is true negatives, FP is false positive, what we call the type 1 error, and FN is false negative, what we call the type 2 error. So this is related to hypothesis testing, just as I had informed you. So once our model has generated these, so what can we do next? So the next thing we can do is we can calculate the accuracy score. And how do we calculate the accuracy score? So the accuracy score is the proportion of the correctly predicted values. So the correctly predicted values should be the true positive and the true negatives, okay? Divided by the total number of samples that you have in your data. So divided by everything. So it measures the proportion of correct predictions, and it ranges in between 0 and 1. So it's simple and intuitive, but can be misleading with imbalanced dataset. So if you are having a dataset that is imbalanced, you wouldn't know which class of the data is contributing more to this conversion matrix, okay? So that's the reason as to why we are saying it can be misleading with imbalanced class dataset. Because if we go over to our notebook, you can see we've got our conversion matrix over here. But on the classification report, this accuracy score that we have over here is not split in between the males and females. So we don't know actually what is the contribution of females in this accuracy score and what is the contribution of males in this accuracy score, okay? So that's the reason as to why we are saying it can be misleading with class imbalanced datasets. And let's say you're working in a loan company. Using accuracy to predict if a person will default or not is actually not good, because in most instances, let's say females are defaults and males are not default. In most cases, you will see, like in class not default, the accuracy will be high, but for the default class, the accuracy will be low, because the number of samples that you would have in defaulted should be less compared to those that have not defaulted. But we will get to see that example when dealing with real-world data, because we'll work with even more data sets and we'll get to see different classification reports that we can get, and we will interpret them better. But for now, just understand how we come up with it. So it's not suitable when costs of different errors vary, okay? So this is an example. So predicting an email spam. So if you've got most of the emails not being spam, then you will have a 99% accuracy. Then let's head over to precision. So what is precision? So you can see over here we've got precision. So what is it all about? So precision, this is the formula. So you are only focusing on the true positive class, and you are getting the ratio of the true positive divided by the true positive plus false positive. So this is your true positive. So you are actually focusing on those individuals that were approved for the loan, and you are comparing them with those that have been approved and those that have not been, those that have correctly been misclassified for loan approval. So those that have a loan denied because the prediction was not loan being denied, those that were given a loan and were supposed to not be given a loan. So that's what precision is all about. So what it measures, of all positive predictions, how many were correct. So this is actually a great metric, because over here you will see, is my model giving me results that are beneficial for the kind of task that I'm working on or not? So it ranges between 0 and 1. So 0 being the lowest and 1 being the best accuracy. And it focuses on minimizing false positives. Okay, so what do we mean by false positives over here? So if we are predicting if someone qualifies for a loan or not, we are trying to eliminate individuals being given loans whereas they are not supposed to be given. So that's what the precision score does. So when the model says positive, how often is it right? So that's what we are trying to check. Okay, so here if we calculate the precision for this example that we have head over here, you can see the model was 99% accuracy. But if we calculate the precision score for this model, you can see that 80% of all emails are flagged as spam were actually spam. So our focus will be to eliminate that 20% that's remaining. And we will not say that our model is 99% accurate. So we will say that it's 80% accurate in classifying spam emails. Okay. And apart from precision, we have recall again. So what does recall measure? So of all actual positives, how many were correctly identified? So here we've got our true positive divided by the true positive plus false negative. So you can see over here, we are now including the false negative. So how many did we misclassify under the false negative class? So this is the calculation of recall. 80% in this case, so 80% of actual emails were correctly identified. Okay, so how do we interpret this in real world? So we will come over here to accuracy. So for accuracy, an accuracy of 99% in spam emails classification means that your model correctly identifies 99% of emails, but misses or incorrectly flags 1%. Then for precision interpretation, so a precision of 80% means that when your model flags an email as spam, there is an 80% chance that it's truly spam. So in practical terms, if you block emails based on your model, 20% of blocked emails might mistakenly inconvenience users. Then recall. So a recall of 80% mean your model correctly detects 80% of actually spam emails. Thus, it fails to identify 20% of spam emails, leaving these potentially harmful messages in users' inboxes. So you can see the difference between precision and recall when it comes to interpretability. So for precision, we are trying to see how many emails did we block that we were not supposed to block, okay? And for recall, we are trying to see how many emails did we not block that were supposed to be blocked. You've seen the difference between precision and recall, so that might confuse you when you are trying to interpret your results, but kindly get this. So for precision, you are trying to look at things that might inconvenience the user, okay? And then for recall, you are trying to look at things that might inconvenience you as a business, okay? So that's what we have. And then lastly, we've got the F1 score. So the F1 score is a harmonic mean of precision and recall. So it's a combination of both precision and recall. So what it does is it balances precision and recall for you. And it's useful when you need a single metric. So when you don't have to explain both recall and precision, okay? Yeah, and after the precision and recall and F1 score, what we have next is the specificity. So for specificity, it's basically the true negative rate, and you can think of it as almost similar to recall, okay? But the thing that you change over here is instead of using FN, the false negative, you use the false positive. So what it measures is of all, so this is specificity, recall is sensitivity. So what it measures is of all actual negatives, how many were correctly identified. So remember, precision is the opposite of specificity, because precision is of all actual positives, how many were correctly identified. Sorry, it's actually supposed to be the negative of recall. Yeah. Then we've got the ROC, AUC, so which is the area under the ROC curve. So we haven't created this, but we will create it. So this plots the true positive rate versus the false positive rate at various thresholds. So 0.5 would mean that this is a random classifier, just making in random predictions, and a model that has a ROC-AUC score of 0.1, it will be a perfect classifier. Then we've got the precision recall AUC, and what it measures is area under the precision recall curve. So these two that you are seeing over here are actually a representation of the precision recall and F1 scores in terms of curves. Okay, so this is the representation of those metrics that we've discussed in terms of curves. So let's have a look at the interpretation of that. So specificity and F1 score. So an F1 score of 80% indicates a good balance between correctly identified spam and avoiding misclassification. So it's a reliable overall measure of performance for scenarios where both false positive and false negatives matter significantly. Then specificity interpretation example. So a specificity of 99% means your model correctly identifies 99% of legitimate non-spam emails. So it mistakenly flags 1% of normal communications as spam. Then for the ROC-AUC curve, so the ROC-AUC score of 0.90 implies a strong capability of spam classifier to distinguish spam from non-spam and correctly ranking spam emails higher than non-spam emails. Then precision recall AUC. So a precision recall AUC of 0.85 is valuable for highly imbalanced datasets, signifying the model effectively identify rare positive cases while keeping false alarms manageable. So the last thing we're going to look at is multi-class classification metrics. So what we've looked at is applicable for multi-class as well. But for multi-class, you can focus on even more. And we can start with macro versus macro averaging. So macro averaging here is where you calculate the metric for each class separately. And that is similar to what we have over here for female, male, and all that here. And then we've got the take for unweighted average. So if you use unweighted average, it means that you're going to create an average based off the values that are being seen, and you won't consider the size of each class. And what you do is you treat all classes equally. So that's for macro average. So you calculate the metric for each class separate. You take the unweighted average. So here you don't consider the size of each class, and that's the reason as to why we are saying you treat all classes equally. And then for micro average, you aggregate the TP, FN, FP, FN across all classes, and then you calculate metric on aggregated counts. So aggregated counts means like what is the sample size. So that is the support number that you are seeing over here. What is the sample size for each class? And then you weigh it by the class frequency for the same. So this is what you will get. So macro F1, and that's basically what you are seeing over here. So macro average. So classification report will always give you the macro average, and what you have at the top over here just the actual values, and lastly you've got the weighted average for all of them. So that's what you have for this last part over here. So how do you choose the right metric for the model that you are creating? So for regression, MAE, you'll use it when you want interpretable, robust metrics. For RMSE, when large errors are particularly bad. So if you are dealing with maybe let's say a time series data, and we can look at an example. So for example, for this competition that we have over here for Zindi, let's say this one. Yeah, you can see they are using the root mean squared error for evaluation. Okay, and why are they using the root mean squared error? Because this problem is, can you predict the nutrient gaps for a more fertile tomorrow? So when you are dealing with crop data, it means that the scale at which your values will be at are quite huge. So you will need an evaluation metric that will penalize large errors, and that's the reason as to why this competition is using that metric for its evaluation. And then we've got the MAPE, when relative errors matter more than absolute. And then we've got the R squared score, when you want to understand model explanatory power. There should be a competition over here that uses the R squared score. Let me check and see if there is one. CPI, that is big. Let me see if there are filters over here. Yeah, plantation counting. Let me see what the evaluation metric was here. Root mean squared error. Let's check these. Yeah, so this is classification. You can see they are using different evaluation metrics. So each competition will have its own evaluation metric. So which means that for each task that you are going to do, will have its own evaluation metric. And from what you are seeing over here, you'll get to note that for the ML and data science tasks that you will be working on, the organization that you will be working for will define which metric is relevant for them. Okay, so let's proceed. For classification, you can have accuracy when the data set is balanced and there are equal error costs. Then precision when false positive are costly, for example, for spam detection and all that. Recall when false negatives are costly. And then F1 score when you need balance between precision and recall. Then ROC AUC for binary classification and balanced dataset, and PR AUC. So for these two, you will rarely find tasks that recommend you to use that, but for these three, they will be used mostly, because you can see over here, for example, for this challenge, it's checking the F1 score and precision score mostly, and then these are the other ones that may be considered. Okay, and then what are the common pitfalls that you might experience when dealing with the regression? Using MAPE with zero values in target values would give you issues. So if your target variables have zeros, then you will have issues, because that is a percentage. So there will be, you will experience issues with zero division errors. Okay, and then when comparing RMSE across different scales, because the values that you will be getting will be in a bigger scale, because here you are taking the roots of the mean squared error values that you have. Then the last thing that you might experience over here in regression is ignoring the residual patterns. Remember, when I was training you, the introduction to regression classes, I showed you how you should look at the residual distribution that you have in your data. So if the residuals are not normally distributed, so what are you supposed to do to fix that model? And what are you supposed to do to change the kind of evaluation metric that you are going to use? So you should consider the residuals, and you should not ignore the residual patterns. So you should check what are the patterns of your residuals and adapt your model to give you better results. And for classification, if you use accuracy score on balanced datasets, then it means the results that you will get will not be accurate, because you'll need to explain for the class that has a minimum number of samples, how is the model coming up with predictions for that class? Are they accurate as compared to the class that has the majority, or is it really different, or is it lacking? Okay, so you will need to use an even better evaluation metric for that part. Then optimizing for wrong metric given business context. So if you're, for example, for these tasks that we have over here, you've seen that we are supposed to use the F1 score. But what if we are dealing with a task that is a language that is LLM based? For example, the Kenya Clinical Challenge that we have over here. You can see it's using a new score called the ROG score. And if we open the ROG measure, you'll see that it's an F1 measure, but specifically created for LLM models. So you'll need to check and see if the evaluation metric that you are working with is good for the kind of task that you are doing, and if you'll need to do a bit more customization to that evaluation metric. Then, not considering class distribution in train and test splits. So when splitting your data into training and test set, I've shown that. I've shown you how you do that. It should be here. Yeah. So we just did a random train and test split. But did we really consider if this data was balanced or not? And how many samples do we have in the test set for each class? Okay. So you should consider that as well when you are splitting your data. Then lastly, confusing precision and recall definition. So you should not confuse precision and recall definitions. I've defined what they are in the notes, so you should go through them all over again and understand them. You can write the interpretation somewhere and at least know what each and every metric means. Yeah, so those are the common pitfalls that you might experience when evaluating your model. So today we are just looking at the theory. So I'll give you time to research more on what I've shown you over here today and see where each and every of these metric has been applied and where they is mostly. So that should be it for today. Tomorrow we will proceed on and look at two new models, and the two new models are the KNN models and the clustering models. So we will look at these tomorrow together because they are somehow similar, and the concepts that are taught over there are a little bit similar. So that should be it for today. You can ask questions if you have any. Anyone with a question? If you have no questions, then I'll stop the class record.